Alright, let's go ahead and get started with this lecture video on enthalpy, sometimes known as enthalpy. Alright, enthalpy is like the theme of thermodynamics. It is one of the most critical concepts. It ties in all of the other lecture videos that you have watched so far. Sometimes enthalpy can be somewhat confusing, so we're going to try to make it as simple as possible for you to understand. You may need to rewatch this lecture video a couple of times just to get it down. Alright, so here we go. Enthalpy really deals with potential energy. And you remember from our lecture video on potential or internal energy, we talked a little bit about what potential energy was. And so potential energy is stored energy in chemical bonds. Because of the electrostatic or Coulombic attractions or repulsions between charged particles, we have potential energy. And so that's what I need you to think about this in your mind, is potential energy is stored in chemical bonds. And it comes or arises, potential energy arises because of the electrostatic attractions between charged particles. Now, this next statement is probably one of the most important statements in this entire lecture video, and that is, the stronger the electrostatic attractions between charged particles, the lower the potential energy and the more stable the system is. So when we have strong electrostatic attractions between charged particles, we create a very low potential energy state. And the lower the potential energy, the more stable the system is. And this is the key. This is really the absolute key to understanding one of the most critical factors in why chemical reactions occur at all, or why anything occurs in the universe or nature, is that we are trying to lower the potential energy of a system to create more stability. And so a chemical reaction is naturally going to occur because it wants to strengthen the electrostatic attractions, the bonds, strengthen the bonds, and therefore lower the overall potential energy and create a more stable system. And this is our goal in science, is to understand enthalpy changes and this kind of becoming stronger electrostatic attractions. Alright, now, because these electrostatic attractions are pretty much dictated by Coulomb's law, we have to understand again that Coulomb's law is going to help us to determine how strong the interactions between charged particles. And remember, the greater the magnitude of charge, the stronger the attraction. And therefore, when you have more charge, you have an actual lower potential energy system, and it's more stable than less charge. Also, distance is really important. As you look here, we've kind of talked about this in our unit of bonding about the distance and electrostatic attractions. But let's see, highlight this is, since making bond process is an electrostatic one, it is governed by Coulomb's law. The distance between attractive charged particles plays a big part in the amount of potential energy between them. The optimal distance between charged particles will result in the lowest potential energy state, called the bond length. And we talked about bond length and looked at this, and this is important. So when you look at charged particles, whether they're ions or whether they're atoms that are going to create covalent bonds, or they're metallic bonding, or whatever. The idea is that the distance has a big factor on the amount of potential energy that the system is going to have. So if two charged particles are relatively far apart from each other, then they're going to have higher potential energy. But as they get closer together, the potential energy is going to drop, as it shows here, as the distance between those charged particles gets closer, to the point where we get the optimal distance, where we get the lowest potential energy state, and that creates the best stable situation for our system. And so this is pretty important to understand, right? Alright, so now, this is where we're going to start really getting in enthalpy or enthalpy and understanding what that means, okay? So when the system is under constant pressure, okay, constant pressure, oops, need a highlighter. When the system is under constant pressure, the total potential energy in chemical bonds or intermolecular forces is known as enthalpy. So really, when we think about potential energy or the total potential energy in a system, we're talking about its enthalpy. And that's just a fancy word of just saying the total potential energy that the system has when it's under constant atmospheric pressure. Now, if the atmospheric pressure is not constant, then we cannot use the term enthalpy. So when we think of enthalpy, we have to think, oh, the system is under constant atmospheric pressure, and so we're dealing with enthalpy or enthalpy. Okay, enthalpy is given the symbol of H. Now, the thing here to remember too is that the total enthalpy of the system cannot be measured. Okay, we can't measure it. There's no. Remember that a thermometer measures the average kinetic energy. It does not measure potential energy. We have no device that measures potential energy, and so we have to use this understanding of enthalpy. And so what we can measure is this. What can be measured is the amount of heat absorbed or released during a chemical reaction or process. Okay? So we can measure heat energy because we can use a thermometer. And a thermometer measures the changes and essentially measures the changes in average kinetic energy as heat is being transferred out of the system or into the system. Alright? Well, it turns out that the change, we call the change in enthalpy, is equal to the change in heat energy. Alright? So what this means is that for a reaction studied at constant pressure, the flow of heat is a measure, it's an actual measure of the change in enthalpy of a system. So if I was to write this down for you, kind of so that you can see this, you can say that heat is equal to the change in potential energy, or the change in enthalpy. Alright? So if you know how much heat energy is being transferred out of the system or into a system, that is going to equal the same amount of potential energy change, or the change in enthalpy. Now, for this reason, the terms heat of reaction and the change in enthalpy are used interchangeably to study reactions under constant pressure. In chemistry, most reactions, just pretty much almost every chemical reaction and pretty much every state change, state from gas, liquid, or solid, is going to be under constant atmospheric pressure. And so we can use enthalpy all the time to understand more or less if a system is becoming more stable, or if a system is becoming less stable based on the change in potential energy. So again, let's look at it this way. Enthalpy is really potential energy under constant atmospheric pressure. The change in enthalpy, which is really the change in potential energy, is equal to the amount of heat energy that is either going into a system or out of the system. Alright, so you're going to need to think about that relationship because it's vital to your understanding of thermodynamics and chemistry as a whole. Alright, so if you need to go back and relook at this video, do so. But this is it for this particular episode. Alright, so bye for now.